Okay, so hi everybody, and welcome to this session of the nuclear reaction seminars. Today's speaker is Dr. Natasha Timofeyuk, who's a senior research fellow at the University of Surrey, who has also worked in the University of Brussels and in sorry, and in the Institute of Nuclear Physics of the Academy of Science in Uzbekistan. She will be speaking today about the non-locality in nuclear reactions. But before we begin with the talk, I would like to go over the logistics. So during the talk, you all will be muted, and we encourage you to leave the questions for after the talk. After the talk, you can raise your hand using the raise hand option that you can find either in the bar under or in the list of participants. When you raise your hand, I will unmute you and you will be able to speak and ask your questions. If the raise hand option doesn't work, then you can try to tell us through the chat and we'll try to allow you to speak anyway. And this talk will be recorded and you will be able to find it as well as past talks in our website. And I think that's all. So now I will let Natasha give us a nice talk. So you can talk now, I think.
Okay, thank you, Mario. Hello, everybody, and welcome to my story. This story summarizes research on DP reactions undertaken at Surrey over the last 8 years, and it tells about what happens if we use non-local optical potential to describe DP reactions. I will tell you the story the way it was unrolling, and I will start with telling you what has triggered this research. So the story started about 8 years ago, and at that time, it was noticed that the spectroscopic factors measured in nuclear knockout experiments were reduced with respect to the shell model predictions. And this reduction was different depending on whether weakly or strongly bound nucleons were removed. But at the same time, those who analyzed transfer experiments such as DP or PD couldn't confirm the conclusions of knockout experiments. Here, I show the results from the paper of Jenny Lee and co-authors, but of course, there are many other papers which investigated this matter. So when you have a disagreement between two different methods, what you normally do as a first step, just try to understand what were the models and what was input to these models. So I didn't do anything about knockout reactions, but I was looking to DP reaction and particularly to this particular paper by Jenny Lee et al. So I'm going through the methodology session, and it says that they use Johnson-Soper adiabatic approximation, so which is fine. So it means that they use three-body model, target plus neutron plus proton, and they try to find the wave function in the adiabatic approximation. This is fine. So then I read, on the locality corrections with range parameters of 0.85 and 0.54 were included in the proton and deuteron channels, respectively. Right, so I look at the 0.85. It comes from the paper by Perret-Bach. Fine, there is justification. And then I look at this parameter 0.54. And I just realized I couldn't find original paper where this number has been derived. I tried to look through different books and just couldn't find out who was the first who said that there should be an locality correction by 0.54. So there was a question where this number came from. So I was walking around the corridor one day and met Ron Johnson, who is the first author of the Johnson-Soper adiabatic approximation. So I asked him, Ron, do you happen to know who was the first who determined that the deuteron non-locality correction is 0.54? And Ron said, but the locality for deuterons is not 0.54, but 0.45. We have shown this in our paper, that the non-locality correction for deuterons should be twice smaller than the non-locality correction for neutrons. So the paper Ron was referring to It's a paper by Johnson and Soper called Relation Between the Deuteron and Nuclear Optical Potential, published in 1972. So there are two Johnson-Soper papers, one of those which is the basic of Johnson-Soper adiabatic model, which everybody uses, and this is another one. So what they were doing there is trying to see what will happen with the deuteron target potential in the Watanabe model when the potentials are non-local. Fine. So the question is, if Johnson and Soper proved that this non-locality correction for deuteron is 0.45, then why everybody else uses 0.54? So it was kind of mysterious, and it was really worth investigating. Before investigating, let us just first of all remind us what is actually this non-locality thing. If you have scattering of nucleon from some target, here is the optical model with no local potentials. If you use local potential, then you don't have here this integral. You just have product of the potential and the function of distance between neutron and target times wave function. But this is non-local model, and we have dependence of potential on two variables. Where all this comes from? And the origin of this non-locality comes from the complex structure of the target. So when actually we do scattering, we excite target and de-excite it. But if we don't want to take this multiple excitation into account and neglect all these coupled channels, then what happens is the neutron kind of disappeared, or from disappears from the elastic channel, goes to some inelastic channel, and then comes back again. And when he comes back again, he comes not necessarily to the same point. So as a result, interaction of this neutron with the target would be some average of interaction with the neutron with all other possible locations. Perry-Bach proposed a model for this non-local potential. They proposed to approximate it by a product of two terms, one of which is exponential and depends on difference between r and r prime. Here is beta is non-locality range, and non-locality range is small, which tells you that it's unlikely that your nucleon will appear some far away from the place it disappeared, times this non-local form factor, which is the average between distance r and r prime. So Perry-Bach also showed that rather than solving this non-local problem, you can solve a simpler problem, which is local problem. And the local potential will be found from the transcendental equation. You solve this transcendental equation in each point r, right? Where you just have this nuclear form factor, local form factor here, and non-locality range. So you can go beyond this leading order, which will involve to add some correction to local potential. And then you need to multiply this local wave function by that exponential. How does this exponential look like? When we are far away from the target, then the optical potential is equal to 0 and the exponential equal to 1. When we are within the target, then it's not 1, so it's smaller than 1. So this is the typical behavior of that particular factor. It's called Perret factor, and that's exactly what is embedded in computer code, which experimentalists are used to analyze DP reactions. For example, this is exactly what has been done in paper Jenny et al. And in many other papers which has been used for the last 50 years. Okay, so all this is related to the two-body scattering. And this local equivalent model has been developed for two-body scattering and also there was a work by Johnson and Soper where they considered what happened to Watanabe model. But the question is, does this local equivalent model, is this model applicable to the adiabatic approximation? Is it legitimate to use the Perret factor when you have not two-body scattering, but three-body scattering? So I was looking everywhere and I couldn't find any work which would justify using of the Perret factor, which exists in many codes such as 2FNR, DUAC5, DUAC4. And that's actually what triggered the whole work, because it was clear that there are models, the computer codes, which are used by experimentalists, who use the option which is not justified. So it was worth looking at it. By that time, of course, Deltuve has published his three-body calculation made in Faddeev model with local potential, with non-local potential, and with local equivalence. And he showed that non-local optical potential and three-body problem with local potential give different results. So it was really very intriguing and interesting, and that's where we started. Okay, so we have DP reactions. Deuteron is incoming on target A, and then neutron is transferred to and become part of nucleus B. And here is the amplitude of this process. So what does it contain? It contains many body wave function of target, of residual nucleus. It contains the three-body function of target, proton, and neutron. It also contains distorted wave of the describing the motion of the outgoing proton. And as a transition operator, we have interaction between neutron and proton. Now, this interaction is very short-ranged, which means that we don't need to know this three-body function everywhere. We need to know it only at the separations between proton and neutron, which are small. And Johnson and Tandy have figured out what happened, how to derive such approximation to find out this adiabatic, this wave function. It was called adiabatic model. In this model, you need to solve the local Schrodinger equation to find the wave function describing propagation of deuteron with respect to A. And the adiabatic potential will include here interaction between neutron and proton, just to show, to accommodate the fact that we don't need to know the function everywhere. So this is local Johnson-Tandy model. But what happens when interaction between proton and target and neutron and target is non-local? Then, of course, we need to solve non-local two-body Schrodinger equation with the non-local adiabatic potential. And this non-local adiabatic potential does not look nice at all. So here we have non-local interaction between neutron and A and proton A. It depends on two arguments, 1 and 2, but these arguments are actually a mixture of the different variables of the interaction between target and center of mass, the same with R prime, and with the interaction between proton and neutron. So it does look messy. Here, phi 1, and the same phi 1 which enters of the local adiabatic model, is the product of the neutron-proton interaction times deuteron. So interesting thing, if we replace in that expression phi 1 by phi d, then we'll get exactly Watanabe model, the same as Johnson and Soper considered in 1972. And then when they were considering this model, they had two scales. One of the scales was associated with the range of non-locality. Another scale was associated with the range of deuteron size. Non-locality range is very small, it's just under 1 Fermi. But the neutron is a very large object, just average distance between neutron and proton is about 4 Fermi. So there is difference of scales, and that helps them to figure out approximations for adiabatic non-local potential within the Watanabe model. But now, as soon as we have here phi 1, so we have another scale associated with the range of the neutron-proton interaction. And this is small. This is the range which compares with the range of the non-locality. So here it's more difficult to make approximations. So you have some time to figure out what can you do about this rather than solving it exactly. But in the end of the day, you realize that it is possible to do an approximation. You use some kind of the Taylor expansions, and you end up with in the leading order solution that all this integral can be substituted by a product of the local potential times wave function. An equation for local potential looks very similar to what Bray-Bacht have derived. The difference is, you of course here use different reduced mass, you have here different non-locality range, which is indeed have the non-locality range of nucleon. You of course here have the sum of the proton and neutron form factors, and some constant in front of that. So equations should be solved at each particular value of distance between neutron and target. We can go beyond the leading order solution. You can have next to leading order, which means that you need to add some correction to it. I don't show any formula here because it's kind of cumbersome, but it's eventually simple. And after you figure out what is the wave function from this equation with corrected local potential, you need to multiply it by something which is basically looks like a Bray factor, very similar. So how good is this approximation? We were able to answer this question actually 4 years later. And this is the work of Greg Bailey, who was at the time the PhD student at Surrey. So here's an example for calcium DP reaction. Black solid line shows you exact evaluation of this integral and using it in DP reactions here. Now, blue dashed line is employing leading order solution, I mean this local potential, and solving local problem. But then you go beyond the leading order, we add this correction and use the Bray factor, and we get very close to the exact adiabatic solution. Here, the difference between next to leading order and exact solution is about 3%. So conclusion is, yes, there exists a local equivalent adiabatic model when you have non-local potentials. But of course the question is this model the same as everybody is using in the available reaction codes? To understand this, let us look again at this transcendental equation from where we determine a local DA potential. And it's very useful to go back to the work of Johnson and Sopa. They have this coefficient M0, which was very close to 1, practically 1. And they shown that in this case, the local equivalent potential can be just constructed from local equivalent nuclear potential taken at half the deuteron incoming energy. Okay. But in the adiabatic model, this M0 is not 1. It's about 0.8 if you use a Hilton wave function to derive it. So what can we do here? We can present this M0 as exponential of logarithm of M0. And we can combine this exponential with this exponential. And we can combine constant in that exponential with the constant in this exponential, which is neutron scattering energy. So it looks like we should get something which will have some of the local potential taken at some different energies. More exactly, if you do math properly, and only for the case when you have the same number of protons and neutrons, so they can use the same optical potential, then you get the following solution. The solution of this equation would be just sum of the local equivalent neutron target optical potentials, slightly modified, but this is close to zero, not exactly, but close. And the taken energy, which is looks a bit complicated. First of all, you can recognize here E over 2. This bit is about 1. This is also about 1, slightly smaller. But anyway, you can recognize E over 2 plus something else, plus something that has meaning of additional energy. And how big it is? Well, it's about 40 MeV. Right, so it looks like we have the answer to this question, that our solution of the adiabatic model is not the same as the model everybody used in the code. So therefore, it will affect the DP calculations. So how it will affect? We can make some predictions before doing any calculations. So it looks like approximately we need to use the optical potentials as slightly shifted, it's quite a shifted energy. When we shift the energy, increase the energy, then the depth of the optical potential is smaller. And that's what happens. Here are examples for a few cases, neutron scattering on oxygen, argon, and calcium. So with the blue dot dash line, this will be the traditional Johnson-Soper calculations using local equivalence taken at half the neutron energy. This is what everybody does. But if you follow the adiabatic model we just derived, you see that the real part will be smaller, actually imaginary part also smaller, which tells you immediately that your cross-sections should be bigger. And indeed, cross-sections are bigger, which means that if you use these cross-sections, these calculations to determine spectroscopic factors, your spectroscopic factors should go down. So I can send you to find out more on the local potentials versus local potential in the works of MSU groups. They here shown what was investigated, what was happening when you use non-local versus local in neutron channel and in proton channel and for neutron bound state potentials. But I will continue with my story. When we first calculated this coefficient M0, we used the Hulten model, and we thought that perhaps the conclusion should not depend on the choice of the nuclear-nuclear interaction. And indeed, we've taken AV18 potential, only S-wave contribution, and if so, that AV18 with only S-wave gives approximately the same with the Hulten does, and we even published somewhere that there is no sensitivity on the choice of the NN potential. But however, it is well known that the realistic neutron models have contribution of the D state. And although the contribution of the D state to the total weight of the wave function is small, it's about 6%, contribution to the potential energy is much bigger. And this coefficient M0 is determined by the matrix elements, which is actually kinetic energy within the range of the nuclear proton potential. The range of the nuclear potential is very small, and when the range is small, it means that kinetic energy they are very big. So therefore, when you include the deuteron this state, you can see that you can give much more contribution to this particular matrix elements. So here is calculations of M0 for various nuclear models, for Hul-10, for rates of core, AV18, CD-borne, and for 5 version of the chiral AFT potential at next to this order with the 5 different regulators. So now you can see when it includes calculated within the full model space, then M0 is very sensitive to the choice of the model. As a result, this matrix elements is also very sensitive, and the shift just goes all over the place. You can shift it either by 35 MeV or by 70. It's just a lot. So here is the illustration of why we have this sensitivity. This VNP times deuteron wave function in shown momentum space. We need to, because of the VNP, we need to take them at small distances where the energy become higher, and at higher energies, the product VNP times 5 goes down, and contribution from this state increases. So contribution to this matrix element is about 40%, not 6%. And of course, this affects the DP cross-section. So here an example for the calcium 40 DP reaction, taken at 11.8 MeV. Results are shown for Hul-10 wave function and for AV18. So the Hul-10 wave function will be here. Here, AV18 is somewhere there. So you see there is some sensitivity to the short range physics. Now, there is even more impressive demonstration of the strong sensitivity of the DP reaction to the deuteron wave function. Here, by turquoise line, we represent all 5 versions of the chiral AFT models. And it is different depending on the quantum momentum of transferred neutron and on separation energy. For some cases, it's really super huge. And the reason why they were shown this particular scale is because here, experimental data are available here. So clearly, you cannot ask experimentalists to use our models because uncertainty is too big. And this big uncertainty feels not right at all, because you can't imagine how can you feel this high momentum components when your incident energy is so small. And you think, what can cause it? And of course, the obvious thing is to see maybe it's the adiabatic approximation itself, because indeed adiabatic approximation emphasizes what is happening at the small separations between neutrons and protons. So you have to go beyond adiabatic approximation. And one of the ways to do it is to use continuum discretized coupled channel method, CDCC. And this was done by Mario Gomez Rames when he came to SARI of his first time. He spent there 2 months. So he derived local equivalent CDCC model, so which means brilliant because you can use Fresco to solve the CDCC equation. And what you need to do, you need to find out what are these local potentials. In the adiabatic model, we had to solve one equation, one transcendental equation. But now, in the CDCC case, to find these local potentials, we need to solve coupled transcendental matrix equations. That's what Mario has done. And here are some results. So with the dashed line, adiabatic calculations are shown for 2 different potentials, one of which is Hul-10 potential and another rates of core potential. So you do see huge dependence on the choice of the NN model. But when you go beyond adiabatic, you see that this difference goes away. Now the difference between two calculations with two different NN models is very small indeed. It still depends on the quantum momentum of transfer nucleons, but it's basically gone. And actually, at the same time as we were publishing our paper, Del Turro has come with his Faddeev calculations, using all the potentials we used in our calculations, and show that there is actually practically no sensitivity to the NN interactions when you solve full equation, non-adiabatic model. Another interesting thing here is when you compare adiabatic to CDCC, either for any potential at all, you see here that the contribution, non-adiabatic contribution, is quite large, much bigger than what happens when you compare CDCC with adiabatic for local potential. For local potential, it will be about 20% in the maximum, 30% maybe, 10, 40, but here is much, much bigger. So what does it tell you? It tells you when you have no local potential, you should not use adiabatic approximation, you should go beyond it. So let us have a little bit different view on treating locality. We go back again to the local equivalent optical model, and we consider it in the next to the leading model. So in the next to the leading order, it has some local equivalent potential, as we already seen, and it has something else, which is actually velocity dependent part, because it contains the gradient of the wave function. So what we can do now, we can try to solve three-body equation, including this velocity dependent optical potential. So we have it for neutron, we have it for protons, and of course we have VMP. So after we have written down this particular equation, we actually can do a Perret factorization of the three-body wave function. It can be presented as product of two functions which basically are Perret factors times some other wave function, which is a solution of the local three-body equation, actually almost local. Here, this effective potential will be very close to original local potentials, and the deviation is basically due to recoil, so that when you increase the mass of the target, this difference will go away. And there is some three-body term. Actually, it is very small, and it also has the recoil nature. The heavier is your target, the smaller is the small contribution. Now, the interesting thing is, when you try to solve this thing, this equation, you neglect small part and solve this equation in adiabatic approximation, you will get up exactly in the same adiabatic approximation which is being used in all reaction codes for the last 50 years. So now we have justification of what everybody is doing, but now we know that this model does not give the same as the full adiabatic model. Right, but we can solve now this equation not in the adiabatic model, but to go beyond it. We can use the same CDCC, and this is what Mario Gomez Ramos has done when he came second time to the University of Surrey. So he solved this equation by using very accurately expressions for all these potentials here and using these small corrections as well. So he was using Fresco, and after that he was multiplying the solution by the Perret factor. The most interesting thing would be to compare his calculation to calculations of Deltuva with the same non-local potentials. Deltuva used Fadeev equation, and his calculations are rigorous. So now we see here these Fadeev calculations, and this is DCC calculations, local DCC calculations using velocity-dependent potentials. And the interesting thing is that they are very close to each other. They should not be identical because we, for example, didn't use the spin orbits, so there should be difference. But here, in the maximum, from the point of view of determining spectroscopic factors, they're basically the same. So perhaps it does tell us something. Perhaps this way was of more exploration. At least it's much easier to solve and to apply for analysis of experimental data. But anyway, when using these calculations in constructing local equivalents, we have taken the optical potential taken in at half of the Newton energy, right? So, but the next question is, how do we cope with the fact that the local potentials are energy dependent explicitly? Because what I was just telling about was everything about the potentials of the Prey-Bach type when there is no energy dependence of local potentials. Local potentials will always be energy dependent because of this energy here. But the question is, are they the same? This depends the same as the dependence of the phenomenological potential. To answer this question, we take any phenomenological systematics and we can figure out this UN. And if this UN does not depend on energy, it would mean that the Prey-Bach potentials give energy dependence of local potentials, which is consistent with phenomenology. Okay, let us do it. Let us take Chapel Hill optical potential systematics. And we assume that U local are known with their Chapel Hill potentials, and we can determine this UN. So what shall we get? We get the following one. Here's the real potentials of UNs, and here's imagined potential. So this graph tells us one thing, that the the energy dependence of phenomenological real potential is the one which comes from the energy independent local potentials. But imaginative part is not. You see, you change energy and changes a lot, which takes us to the next question. How do we take into account energy dependence on optical potentials when we employ them in DP reactions? Of course, the first questions will be how to write correctly three-body Schrödinger equation when you have energy-dependent optical potentials. And to answer this question, you first of all need to understand what the optical potential is. And it was Feshbach who explained to us. In the case of the scattering of nucleons on target A, we have many body wave function which can be represented by two terms. One of the terms is just product of a ground state wave function of the target times relative wave function plus all the other terms, which includes all possible excitation of the target. So Feshbach introduced operator P and Q will project it to everything which we don't want. But we do not want to consider many-body problem. We want to study only two-body problem, in which case this relative function comes from the two-body Schrödinger equation with some optical potential. And the expression for optical potential is the following. It just has some energy dependence here. And of course, it has contribution from all the excitations. Now, we can do the same stuff for the three-body case. We can consider three-body scattering. We consider the total wave function, which is a many-body object. We can also present it as a flashback did by two terms, one of which is the product of the ground state wave function times something looks like the free body part, plus the other term, which contains all possible excitations of the target. And once again, we say that we don't want to solve a many-body problem. We are interested only in three-body problem. Okay, in which case, we found this function high from the three-body Schrödinger equation, which contains NP interaction and then some expectation value of the optical operator. And now for the three-body case, this optical operator will contain all the interactions between neutrons and protons and targets. But what we would like to do is to separate terms which contain only interaction of neutron with the nucleons of target A, and terms who contain only interaction of P with the target. If we do it, we come to the following presentation of the optical operator. It contains something which looks like two-body terms plus infinite series of the multiple scattering terms. So here, for example, these terms will be describing interacting of a neutron with target. Then all possible target excitation goes to protons, and so on to all orders. So we see the difference between two-body case and three-body case. Now we have not only the interactions which looks like two-body interaction, but also some three-body induced three-body terms. Of course, in the first step, we would like to neglect all of them. And we would like to solve the three-body equation with something which looks like two-body interactions. And let us compare the two-body interactions in the three-body system with the optical potentials. Now you see here interactions are the same, Hamiltonian is the same, energy of the A is the same, but what is different is this part in the propagator. So you can see immediately that the two-body force in three-body system differs for two-body optical potentials. For example, it explicitly depends, if we take the interaction of a neutron with the target, it explicitly depends on where the proton is. And it depends on the interaction of a neutron proton as a parameter. And it doesn't contain, it contains three-body energy as opposed to energy of the scattering in the two-body case. So what shall we do in this case? And it turns out we can deal with these operators in the adiabatic approximation. Because in adiabatic approximation, we don't need to know all of the operators. We need to know only these operators when the neutron is very close to the proton. And now, at this point, you have to do a lot of maths. But when you've done it, you came up with this equation. It also contains all this very similar information, and it contains some constant here, E effective. And this effective E is half the neutron energy plus something which we have already encountered when we try to understand the local equivalent model. It's the NP kinetic energy in neutron. And we have seen that it will depend on the NN interaction, and it will vary somewhere between 44 and 120 MeV. If we now compare this averaged potential with the expression for the optical potential operator, we can see they're identical. The only difference is the value of this particular constant here. So this tells us, so the free body problem in DP reactions should be solved with the energy independent potentials taken at effective energy equal to half the Newton energy plus some shift. Okay, let us do it. Let us take Giannini-Rico global optical potential. This potential has energy-independent real part and energy-dependent imaginary part, such that when your energy is zero, absorption is zero, and then it gradually increases to 17.5 MeV. If we're using traditional Johnson-Soper ideas and taking the potential as a sum of the potentials, nuclear potentials at half the Newton energy, then we would have evaluated this imaginary part at small energy, and we would have get big cross-section. But our model tells us we have to take it as a shifted energy, at a higher energy. And if we take some higher energy, for example, the one which obtained from the Hulten-Neutron model, shifted by 57 MeV, absorption is now much larger and the cross-section is smaller. Okay, we can take another potential, which is the local dispersive optical model. There, the energy dependence of imaginary part and the real part is very different, and the results are very different. So if we were using traditional Johnson-Soper model, we almost will have been just bang on the data. And if we use shifted potential, we would have been much larger than the data. So these two pictures completely different, but if you take U local here and U local there, in both cases, results are kind of consistent, more or less. So what's happening here? It's obvious that the cross-section is too big. So what's missing then? One of the obvious thing is that we have neglected multiple scattering. There are some other terms of the optical potentials. Is it possible to recover them? And actually, yes, if we try to recover only this part, it's relatively easy to do. So if you do maths again, you'll realize that in the adiabatic model, the average of operator U0 and U1 will look very familiar. The difference will be this little factor of 2 here. So what you can do here then, you can represent VNA as 2 VNA minus VNA, and you can see that the matrix elements in the presence of next to leading order multiple scattering will be 2 matrix elements of the two-body optical potential minus something. So how do we relate all these to phenomenological optical potentials? Phenomenological optical potentials have Hartree-Fock part plus some dynamical part. Dynamical part would have some imaginary part plus something, some real part which comes from imaginary part by using dispersion relations. Now, if we associate these matrix elements with the optical potentials and this part with the Hartree-Fock part, what we'll get that in diabatic approximation, the optical potential we need to use are just Hartree-Fock part plus 2 dynamical parts, and which should be evaluated of some effective energy. Okay, let's try us do this. And this is the work of Michael Dinmore, who just passed his viva at Surrey a couple of weeks ago. Here we have a local dispersive optical model, which does have dynamical part. It has real part, which is related to imaginary part. So here will be original calculations with the shifted energy, Hartree-Fock plus dynamical part. But if we double it, so in other words, we double the absorption, the cross-section goes down, bang on the experimental data. An interesting thing is that actually, if we double only imaginary part, we get the same result. So when we're doubling imaginary part, it looks like this small dynamical real part doesn't play too much role, which actually interesting result, because it means that you can use other systematics of optical potentials which do not use the special relations, and you simply can multiply their imaginary parts by a factor of 2. And here's example with the Giannini-Riccò-Zucchiati potential. So this will be calculations. We have real and imaginary part. And if we double imaginary part to take into account this induced three-body effect, the cross-section goes down. For comparison, we take also here Giannini-Ricco optical model, which is energy independent. Yeah, the difference is very small. So these results kind of nice, but now I will show you something which is not so nice, and it's the same reaction at 56 MeV. First of all, I would like to pay attention to experimentals, that there are 2 sets of experimental data available. There's no way we can know which one I should believe, so we'll put both the experimental data here. So, but once again, the situation is the following. We take Hartree-Fock plus dynamical part. We get the cross section is too big. We multiply dynamical part by the factor of 2. The cross section goes down, and we get exactly the same result when we multiply only the imaginary part by factor of 2. And the results for Giannini-Riccò-Zucchiati potentials results are kind of similar. So what I've learned here is that the nuclear target interaction in the three-body systems are not the same as nuclear A optical potentials, and that induced three-body effects are important. But we are still missing other multiple scattering terms, and which is perhaps maybe more importantly, we do not have non-adiabatic effects when we consider energy-dependent optical potentials. So we have an outstanding problem: how to use optical potentials in three-body systems, or how to link properly many-body and few-body degrees of freedom. It's very important questions because, first of all, phenomenological systematics of non-local potentials are being established. There are many groups which are working on it. Sorry, I don't give names, but there are indeed many groups here. And so how do we use these potentials? And of course, there are ab initio developments of optical potentials. I have to mention at least Sari group here, and Carlo Barbieri and Andrea Dini work when he was here. Sorry. But of course, there are other groups which are developing optical potentials. And not only from an initial perspective, but just microscopic optical potentials. For example, we heard about it last week. And the question is, what should we ask of these people? Give us potentials as half the neutron energy, or at half the neutron energy shifted by some number? By what number then? And how to treat them at all? I was talking about DP reactions, but three-body models also are used to describe breakup reactions, knockout reaction, cooling excitations. They also use the idea that these many-body systems are described by three-body models with pairwise interactions. So as we have just seen, if we try to project many-body models in the three-body channel, we do not have these pairwise optical potentials. We have something more complicating than that. And of course, it's also very relevant for three-body bound states. For example, lithium-6, helium-6, right? Also, the idea is that three-body wave function of helium-6 is described by three-body function, where you have pairwise potential describing the property of the two-body systems. But once again, if we project many-body wave function of helium-6 into a three-body channel, we have three-body operator, which is different from what is used And the same is relevant for lithium-11, beryllium-14. It is relevant for description of continuum in these three-body states, such as, I don't know, helium-6 excited states in the continuum, beryllium-16, and so on, resonance states. So it looks like there is no justification to use this three-body model. And on the other hand, everybody who used the solved three-body problem with the pairwise potential would tell us that it's a very good model, that it describes a lot of experimental data, and it's something which is very useful. So why does phenomenological description of three-body reactions and bound states work? So perhaps it tells us that there is another way to rearrange three-body operator. Maybe it's not a unique way, but at the moment, we don't know what to do about it. So all this was related to description between many-body and three-body degrees of freedom on the level of optical potentials. But of course, there are other ways of interplay between three and many-body degrees of freedom, and I can send you to our review where we discuss this problem. It is published as open access, so everybody can download it. So the whole story started by trying to understand this simple number, 0.54, used by experimentalists who were analyzing the data on TP reactions and using this correction for non-locality. It was not clear why such description would be justified. Now it's clear. Such description corresponds to the using local equivalent model in the next to leading order, which contains velocity dependent forces. However, exact adiabatic calculations will give completely different result. And these adiabatic calculations with non-local potentials has an artifact. They have a very strong sensitivity to the high momentum between neutron and proton and deuteron. So when we're using non-local potential, we should go beyond adiabatic approximation. But the problem is even wider. The potentials, non-local potentials of themselves, they are energy dependent. And here we don't know how to treat this energy dependence properly. We have developed a adiabatic description for this case, and we showed that the contribution from beyond the two-body approximation is very important. So the question remains, how to treat NP and NA interactions beyond adiabatic approximation, and why phenomenological three-body description of three-body reactions without three-body force are successful. So I hope that somebody who listened to my story would be excited about these problems and will be able to continue this story to the future. And meanwhile, I thank to everybody who came to listen.